Hello, welcome to our presentation on CFD modeling of oil spill trajectory. This is my team, Nathan and Sandra. They'll be working on ANSYS modeling, and myself, Suman. I'll be taking care of the MATLAB under the guidance of Maram Shafai. And here's our content. This will be an overview by Nathan. Then we're going to discuss about the ANSYS result by Nathan and Sandra. Then we'll head over to MATLAB result by me, and then we'll go to the conclusion. Yeah.
Hey guys, so for the overview, so the why, the reason we're doing this is we're trying to accurately predict the trajectory of an oil spill uh, in a faster method that's more computationally efficient. Because the faster you can model an oil spill, the faster you can apply emergency response to clean up the oil. And then how we're doing this is we're going to be modeling the oil domain as a monophasic case of just water and oil particles, which will significantly reduce the time that we need to plot an accurate trajectory. And then we hope that these improved methods will provide an accurate trajectory prediction at a lower computational cost, which will allow for quicker emergency response. So the key points that I focused on for simulation are modeling tidal current as a time-varying inlet velocity function, modeling wind effects and small waves at the water surface as a time-varying shear stress condition, modeling rotational effects via applying a rotating reference frame, and modeling the domain as a monophasic case of water with injection of oil particles. This is my mesh. The boundary conditions are the same as those listed on the left diagram. The key point here is that the top of the domain is modeled as a transient shear slip wall. And then this domain is scaled down by a factor of 1,000 from the one in the study. These are the equations being solved in ANSYS. They're the continuity and momentum equations with terms for rotational effects, again, modeled by applying a rotating reference frame. These are my functions for varying inlet velocity and shear stress at the top of the domain. So we can see that inlet velocity and shear stress change over time. These are the results I obtained. So we can see that my velocity field after 300 seconds of the ocean currents are in good agreement with the results obtained in the study. So we can see that we have velocity traveling in this central part here similarly. And then we also have dead spots at the same areas. So on the left and the right over here, and this pressure outlet pulls some velocity that way. This is my oil slick results. My trajectory was measured at intervals of 50 seconds. So we can see this blob moving here, and then it comes up in beaches on the coast of the domain over here on the left side.
So one of my key points was to model the velocity at the inlet as a varying velocity due to the tidal current. I also modeled the wind effect as equivalent shear stress so that we could see how that affects the oil particles as they move as well. I also modeled the oil particles as discrete particles, and another thing I was focusing on was to get the oil trajectory. So I modeled, this is my velocity profile in ANSYS, and it really does match what was done in the paper. When I simulated the velocity profile at the start, it does match what was in the paper, what was simulated as a result from the paper as well. And then for my oil trajectory, I know after simulating it over time at the end of the simulation, the oil particles tended towards the left side where the beach was, which does correlate with what is happening with the trajectory of the oil particles in the paper as well.
Thank you, Sandra and Nathan, for taking us through the ANSYS discussion. Coming to the MATLAB, here are the result about the shear stress at the sea surface due to the wind on the left and the velocity at the inlet on the domain at the right hand side. And the left one, the first graph indicates the variability in the x and y direction of components of shear stress, which would be due to the change in wind speed and direction. On the other hand, the second graph shows the velocity at the inlet of domain over like 30 hours time period, and the positive and negative of the line flow is mainly because it indicates the water into the domain and moving away from the domain. And this graph, we have two plots on left, which is the surface velocity induced by the wind. The lines increase in the velocities as the wind speed increases, and the total induced velocity is crucial as it illustrates the impact of higher wind speed on the surface velocities. And on the other graph, which indicates the total surface velocity induced by the wind, the x component has a significant peaks and drop, which can be seen by the graph, and the y as a smoother trend, and the total induced is just because of the intensity of combined effect of x and y components. And this is the MATLAB simulation which I performed for the oil spill over different time period. And this video link is provided in the description below. And these are the MATLAB equations which I've used for the velocity components in XMY direction or the Stokes drift, and for the velocity at the inlet, and these are the modified logarithm for the roughness which I've used for the graphs. And yeah, this is the conclusion of project. And Nathan.
So in conclusion, our model successfully provides an accurate trajectory prediction at a reasonable computational cost, similar to what they were hoping for in the study. We wanted the computational cost to be lower, but it seemed to just be about the same as what would have been achieved with simpler Lagrangian methods. But hopefully with improvements in computational power in the future, we'll be able to use these methods to achieve an accurate trajectory at a lower cost.
These are the references which I've used for the answers and MATLAB. And yeah, thank you for taking your time and listening to our presentation. Thank you.
Thank you.